Good day. I'm Dr. Arnold Rix from the Center for Renewable and Sustainable Energy Studies at Stellenbosch University. For the past 6 years, I've been involved with renewable energy projects, first building watt wind turbines, 2.5 megawatt wind turbines, and then I moved over to the utility scale solar PV space. Today, I'll be presenting some slides on photovoltaic systems, and we can have a look. So this is a project for Etiquette Municipality, and the Energy Office commissioned this, and you can have a read through there, the background. Then there's some background about the Center for Renewable and Sustainable Energy Studies that was established in 2007, and I'm not going to read through everything. You can do that on your own time. So first we will look at the PV cell, then move on to PV modules, strings and arrays, and we have to mount these somewhere, so we'll look at some mounting structure options. We'll go on to inverter basics, and to do a correct PV array sizing, we have to forecast the yield. We'll move on to metering configurations, look at the standards and regulations that's currently in place in South Africa, go on to different system configurations, grounding and lightning protection, and then also talk about installation safety, some troubleshooting pointers, and then I'll cover some frequently asked questions. So the starting point of most photovoltaic devices is pure crystalline silicon. Other important materials include boron, gallium, cadmium, and tellurium, and these are used for doping. The difference between conductors and semiconductors can be described using energy band diagrams. The top energy band is called the conduction band, and it is electrons in this band that contribute to current flow. The conduction band for metals is partially filled. For semiconductors, the conduction band is empty at absolute zero temperature. At room temperature, only a few electrons in silicon exist in the conduction band, but by adding impurities to the pure silicon, the conduction capability is increased. For photovoltaics, the energy source to move electrons to the conductive band is photons of electromagnetic energy from the sun. When a photon with enough energy is absorbed, a single electron may jump to the conduction band. 48% is the approximate absolute maximum fraction of photons that can be converted to electrical energy. On the right, you can see a diagram showing the energy that's available from the sun, and this is the yellow going over to the red, and the darker green is the energy that can actually be absorbed by silicon photovoltaics. When we have these positively and negatively charged semiconductors and we layer them, we form a p-n junction or a photodiode. When this is exposed to sunlight, current will flow, and the magnitude of current will be directly proportionate to the irradiance. A current source is used to model the current flow of electrons when photons are absorbed. A diode is modeled because there is a p-n junction formed by the N, which is the negatively charged, and the P, which is the positively charged type materials that is used to form this photovoltaic cell. The short circuit current is also the current of the current source, since no current flows through the diode when the voltage is zero. So when the voltage is zero, this means that there is a short circuit at the terminal. No current will be flowing through the diode. All the current will be flowing from the current source through the short circuit. The open circuit voltage is when all the current flows through the diode. so there is no connection at the terminals. When all the current flows through the terminal, we basically measure the on voltage or the forward bias voltage of the diode. So the effect of temperature on the IV curve and on the power versus voltage curve can be seen in the figure on the right. When temperature increases, the current increases very slightly. You can see here that, well, you actually can't see it here. That is how slight the current increase is with temperature. The voltage, however, decreases considerably with the increase in current. And because of this, the power will decrease with an increase in temperature. Today, the PV technologies that captures almost 90% of the market share is wafer-based silicon, which consists of monocrystalline, and they are more expensive, but they have higher efficiencies, and then multicrystalline, which has a slightly lower cost, but also has a lower efficiency. Then there's thin film technologies, which has a simpler manufacturing process than the crystalline modules, and this makes it a little bit cheaper. And it also has the advantage that it has less degradation of performance due to an increased temperature. So the temperature coefficient is a lot lower than the silicon cells. So now we know what a cell looks like. Now we need to go to a module. To go to a module, we connect cells in series. When we connect cells in series, we add the voltages of every cell together. And here we have an example of 36 cells connected, and in black is the IV curve of the 36 cells. So as you can see, the current stays the same, but the voltage increases. Here we have the IV curve in green of a PV module and the power curve in red of a PV module. And here we can see the maximum power point, and that is at the voltage of the maximum power point and the current of the maximum power point. And this is also information that is given in the datasheet. So if we have one module and we want to create more power and match it to an inverter input, we can connect modules in series to form a string. And this basically, as we connected cells in series, will just increase the voltage, as we see here. We can also add modules in parallel. What happens when you add modules in parallel is that the current increases, but the voltage stays constant. To match the input of PV to an inverter input, we can connect modules in series or in parallel, as can be seen here. With modules connected in series, we increase the voltage, and modules connected in parallel, we increase the current. A very important thing to consider when looking at an installation site is shading. So shading of even just one cell can be detrimental to the performance of your PV array or string. To mitigate this effect, bypass diodes are normally incorporated in PV modules for groups of cells to help mitigate the effects of shading. Here we can see that if you have no shading, the IV curve is in red. If you have 50% shading, an IV curve like the blue one is outputted. And if you have 100% shading in a cell and you use a bypass diode, the green IV curve is the resultant. And on the right, you can see what effect it has on the power. If we, however, go to a string of modules and we look at a cell that's 50% shaded or 100% shaded, we see that the bypass diodes greatly mitigates the effect If we go to a string, however, we see that the bypass diodes greatly mitigates the effect of shading. Here we can see that if we have no shading, the power is 1.741 kilowatts for this string. If we have 50% shading, we have a little bit less power, and even at 100% shading of that one cell, we've got the same output power as when we had 50% shading. So when we look at PV modules and we look at the data sheets, there's certain parameters that we need to consider. All these parameters are normally given at certain conditions, which is standard test conditions or STC, and those conditions are specified typically on the data sheet, which is at 1000 watts per square meter irradiance and 25 degrees Celsius temperature. Then we can also look at the normal operating cell temperature. The maximum power of the module is given, the open circuit voltage, the short circuit current, maximum power voltage, the maximum power current, and then also the temperature coefficients for the current, the voltage, and the power. What you will also find on the data sheet is the warranty of the module, as can be seen on the right here. This module is from Trina Solar and it has a 25-year linear power warranty. So make sure that you're familiar with the warranty and what it actually means. Then what's also given on the data sheet is the module dimensions, the weight of the module, which is very important when looking at the structures it needs to go on, and the cables and connectors that the module has. So the structures to use for PV modules are quite different. We get, as in the picture, utility scale solar plants that use fixed tilt installations, and this is also typical on a rooftop installation where you have a fixed tilt angle, and in the northern hemisphere PV panels faces south, and we are in the southern hemisphere, so we face our panels north. Here are some pictures of a fixed tilt installation being made in the Northern Cape, a utility scale solar farm, showing the people installing the modules on the frames. We also get single axis trackers, and these trackers can be either horizontally installed or could be facing the sun at a certain tilt angle, and then they will follow the sun from east to west. You also do get trackers that tracks north to south or south to north, but typically on utility scale plants we use east to west trackers. Then we get dual axis trackers, and dual axis trackers can track the sun east to west, so when the sun rises it follows the sun till the sun sets, but it can also account for seasonal variability in the sun. So it will also follow the sun from being low in the sky in winter to being high in the sky in summer. For rooftop we get slightly different structures. We get a ballast based, which is a plastic molding that can be folded and be secured onto a flat roof with sandbags or screws or something similar. And then we get lots of different types of structures that can be installed on existing roofs, making use of your IRB roof sheets or your tiles on your roof. So do a good investigation on this, but you'll probably need somebody that's more familiar to give you some advice. So what do we look at when we look at structures? Well, the weight of the PV module is important, and typically a structural engineer must sign off so that he agrees that the supporting structure of the roof is actually strong enough to support the weight of the PV modules. The ease of installation. This is important to installer because the easier they can install, the faster they can install it, and the less they have to pay in wages. Then the durability. A good installation can last a long time, but a bad one will give you headaches. So make sure that the material used is protected for corrosion, it can handle the wind loading, and that it doesn't impact the waterproofing of your roof. If something goes wrong, you also need to look at future access. So if a panel breaks, if something drops on it and it needs to be fixed or it needs to be taken out and replaced, is there easy access to this? Ventilation is an important thing. So the cooler the panels, the more efficient they are. We just saw that the higher temperature decreases the power output. So it's important not to install the panels flat on the roof, but that there is some space between the roof and the panels for proper ventilation. And then obviously cost. You won't take a very, very expensive structure when you can do everything with the same quality, durability, and weight if you can have it at a lower cost. So now we've done PV modules and we've done the structure, and now we need to connect those to an inverter. So quickly we'll look at the inverter basics and how does an inverter work, because PV modules provide DC power. Typically, to connect an inverter to the network, the inverter is an AC source like the network is. So here we have the inverted model as a AC source, and we have the grid modeled as an AC source. These two are connected through wires, and this is typically your network outside, lines overhead or underground, and these wires are modeled as inductors. And the output energy can then be controlled by controlling the voltage vector of the inverter. Now on the right we see a vector moving around, and the engineers in the room will recognize this. For those others, you can look at the top one, because the voltage or the current vectors translates into a sinusoidal AC waveform. The AC source for an inverter is then substituted with an IGBT or MOSFET to create a full bridge inverter, and then also use an output filter to filter the output. And you'll see now why we need the filters. So on the DC side, we have the input from the modules. Then we go through a couple of switches using pulse width modulation. That is filtered, and the output is a nice sinusoidal wave connected to the grid. Pulse width modulation is used in an inverter to generate a sinusoidal output voltage and current. This is done by comparing a sinusoidal wave with typically a triangular wave. When the sinusoidal wave is larger than the triangle wave, the output will be high. When the sinusoidal wave is lower than the triangle, the output will be low. And so you can create a sinusoidal wave. Here we have a bus voltage of 400 volts. So we have plus 400 and minus 400, and when this is switched and put through a filter, we see that we have a nice sinusoidal output. We can then manipulate the amplitude of that output by manipulating the length or the width of the blocks of the PWM output. Here we can see the output after it's being filtered in red, and the switched output that's showed in green. So comparing inverters, we must make sure that we compare apples with apples, and there we can look at the DC input the AC output, the protective devices that's included in the inverter, make sure that you have a good look at this, because there are some devices required by regulations. Some inverters come with those devices and some will not come with those devices. The warranty, the dimensions of the inverter, and the inverter weight. And then some inverters will have extra features like certain communication protocols, monitoring capability, and other management functions. On the right here, we have a typical inverter efficiency curve, and on the data sheet, they will probably not give you this curve, but they will give the highest value of this curve, which will be sitting around 97%. At lower powers, the inverters will be less efficient, and at very high powers, up to 100% of rated, it might also decrease a little bit. But typically at around 50%, 50 to 100%, you would have the highest power. This is just an example curve I took from the web, and you can look on your inverter manufacturer's website if they actually give this curve. We want to operate the PV panels at the maximum power point. Maximum power point for different irradiance levels are shown here on the IV curves with the red dots. If we connect a fixed resistive load, as shown here by the red line, and the irradiance levels change, the modules won't be operating at their maximum power. So this is also why we want to have an inverter with a maximum power point tracker, and this is done by controlling the DC bus voltage. This is the voltage that the modules see. By controlling this DC bus voltage, the current will then be controlled and we can operate at the maximum power point. So before we can decide how many PV panels we need to put in our installation, we need to do a yield forecasting so that we can match our PV installation to the load we have. Yield forecasting is used to obtain the potential of a PV system in a certain area based on the weather conditions in that area. On the right here, we can see a map showing the irradiance levels in South Africa. This map was done by SolarGIS, and the data is also available locally for purchase. So where can I obtain data to do some yield forecasting? Well, irradiance data you can get from ground measurements, or you can get data from satellite derived information. Then ambient temperature is important, and therefore we can use a numerical weather model, or we can also use ground measurements. Wind speed also affects the temperature, and this we can get the same way as we get the temperature. And then soiling we can get by doing on-site measurements, and there's various models that takes care of soiling. Depending on the amount of precipitation, soiling will vary on the conditions. If it's very dusty, there will be more soiling. So for those of you that does not know, soiling is basically dust or dirt that collects on the PV modules and prohibits more light going to the semiconductor material. So when you get this irradiance data, there's a couple of terms that you might not be familiar with. First off, we have global horizontal irradiance, and this includes all the sun or the irradiance from the sun, direct irradiance, or diffused irradiance, so going through a cloud. Normal silicon based PV will still generate power when it is overcast. So if you did not know that, if there's any light going onto the PV, it will generate power. It might not generate full power, but it will still generate some power. Then we go to LTI or GTI, which is latitude tilt irradiance or global tilt irradiance. And this is basically when your PV module is tilted to an angle equal to the latitude. Then we have direct normal irradiance. This is when the module is tilted in such a way that the sunlight is normal to the panel. So it's directly on to the panel. This is very important for the concentrated solar power technologies, but for PV it's not so important. We can have diffused light. And then diffused horizontal irradiance or DHI, and this is typical what you will have in a completely overcast day. If there's some class, there will be components of diffused and direct light. So, as previously said, modules should face north for maximum yield and be tilted to approximately the latitude angle of the location for optimal annual energy. Available yield forecasting software is PVSYST, and this is an industry standard software tool, but you have to pay for this. You also get PVSol, the Solar Advisor model, and this is also free to download, Sunny Design, and you can go to this website to see a more comprehensive list of software available. So if we know the yield we can get, we also need to look at the load. Often it is not financially viable to generate more than the customer can consume because meters does not run backwards or the utility feed-in tariff is low compared to the energy charge. Therefore, it's necessary to try and match the PV generation to consumption. And if you do some financial modeling, you will see if it's viable or not, depending on the feed-in tariff. So we need to look at the PV system's daily profile when matching PV, and then also look at the load. When looking at the daily PV profile, we can see here in green and blue. So the green will be a typical sunny summer's day, and the blue here is typical in winter. We have a slightly lower irradiance, and this is due to the tilt angle showing 0 degrees, and here we have an azimuth of 90 degrees. So the azimuth also shows in which direction the PV modules are facing. This is facing north, so we will have the peak values of the power roughly in the middle of the day. When it's facing west, the peak power will shift slightly to the evening or the morning. Here we're facing west, so to the side where the sun is setting, and here we can see that the maximum power is slightly more towards the evening. Then we need to look at the customer's daily profile, and it's best if you have more information to do the matching. On top we have a fruit packing facility, and we can also see in orange and brown the load of the facility during the different months of the year. Compared to that, we have at the bottom an office building where it's typically relatively constant throughout the week, and it might change over weekends or public holidays when the office building is not completely utilized. The PV system's monthly generation profile is defined by solar irradiation and the PV panel positioning. So we might have at a 0 degree elevation, this is panels that is flat, so it's horizontally positioned on a flat roof or outside somewhere, you would typically see that the generation is higher in summer and lower in winter, and this is because the sun sits higher in summer than in winter. If we increase the tilt angle to 60 degrees elevation, we will see that in summer generation is now lower, but in winter we have more generation. So an optimal angle to get the best annual yield would be equal to the latitude of your location. We can then also look at the customer's load profiles to match the PV, and on top we have a fruit packing facility again, and at the bottom we have a typical farm which irrigate the crops, and we see in our winter months here in the Cape there is rain, so in June and July we don't have to irrigate and there's no power usage. So let's look at an example of a 300 kilowatt PV system, and here we've calculated the power generated, or the energy generated, from the system, and we indicated that in green. Now for all the months we can see that the green supplements or subtracts from the energy used, and there's only a little bit in the October month that might be fed back into the grid. Now if we used the same site and we increase the system size to 600 kilowatt peak, we see that in September and October we are now feeding energy back into the grid. Now this might have no financial benefit depending on the feed-in tariff of your municipality or if you have an Eskom tariff. So this needs to be carefully modeled so that you can see what your financial viability of the system will be. So it's very important to match PV to the load. And the most accurate is the comparison of historic hourly consumption data to the estimated hourly PV generation. So this you will get from metered data. Second best is monthly totals per time of use period data. And then the worst case is if you have only month totals. So this is typically what you would have at your house in a residential area. It's just the monthly total. What you need to do if you only have monthly total is really consider what load you have running, and also do a proper estimation on when these loads will be running the most to see how much PV you should be installing. Now if you've installed PV, you need to meter this to get any feed-in tariff, and meters can be connected in different ways. You do get net metering, which you only have one meter, and the energy that is used and the energy that is exported goes through this 1 meter, and it basically works as a old rolling type meter where if you use energy the meter rolls forward, and if you export energy the meter rolls back. Then you get bidirectional metering, which is an upgraded meter. The installation will look the same, but now energy going in or out of the meter can be measured differently, and the customer can be compensated for the excess energy. Then we have separate metering, and this is more flexible than bidirectional because it allows for the reimbursement for all energy generated or for only the excess energy generated. And then we also get the separate embedded metering, which is the same as separate metering, and this is used when it's impractical to connect the embedded generator meter directly to the utility. So this is if you don't have access to a connection point where the utility meter is connected. When doing an installation, careful consideration needs to be given to the standards and regulations. Currently, we have the NRS 097 standard that focuses on embedded generation. And here the key drivers are low voltage networks designed for power flow downstream. Incorrect interfacing can affect network performance and the quality of supply. And this includes over voltages, voltage dips and spikes, interruptions, harmonics, etc. A very important thing is safety, and this is basically what all the standards and the regulations are about, is safety. So equipment needs to be installed correctly, and if you don't comply with the technical standards, you might also put the network at risk, and this have other safety implications. So a customer can't energize the network while the network is down. So this basically means when there's a blackout or load shedding, you must not be able to feed energy back into the grid. This is a safety risk because if the municipality or ESCOM switched off the power because they're doing maintenance on the lines and you feeding energy back into that grid, they don't know about you and the network is actually live, and perhaps something happens and they don't follow the safety protocol to procedure, there might be somebody that gets hurt. So that will be under consideration. Then we have NRS 097-1. This actually does not exist yet, and it should describe the embedded generation connections to medium voltage and high voltage networks. This will be based on the ESCOM standard for interconnection of embedded generators. This is a standard that currently does exist. It complements the SA grid code, and it gives the protection details, the anti-islanding details, the SCADA details, and the metering details that is required. Then we have NRS 097-2. This is a small-scale embedded generator connection to low-voltage networks, and it covers a set of industry standards. The 097-2-1. Edition 1 is published, Edition 2 is being reviewed, and we're waiting for publishment of that. Edition 2 is in draft format currently, but it might not be taken further. Then we have the utility framework, NRS 097-2-3, and this is published. Then we have procedures for implementation and application, which is 097-2-4, and this still needs to be developed. So 097-2-1 is the utility interface, and this is where it's described where you must use an inverter that's approved. Installation must be compliant, like for example the labeling done, so that anyone coming in can see that this is a DC source connected and not an AC source. This basically gives an electrician doing work in your house a heads up not to connect any AC wires to DC wires. Then NRS 097-2-3 is about the utility framework, and this restricts the maximum amount of PV based on a supply size. So if your house has a 60 amp circuit breaker and a notified maximum demand of 13.8 kVA, you are only allowed to connect a PV generator to the size of 3.68 kVA. Then this regulation or standard also dictates how much can be connected to a certain line, and here we can see if you have a total energy on an MV feeder, so this is medium voltage, typically ESCOM, you can have a total embedded generation of equal or smaller than 15% of the medium voltage feeder peak load. This is to make sure that you don't overload the transformers or the lines. Then going to the low voltage side, it depends on if you have a dedicated feeder or if you have shared feeders. Dedicated feeders can have a embedded generator of almost 75% of the notified maximum demand, and if you have a shared feeder, you can only have up to 25% of the notified maximum demand. Standard 097-2-4 will basically list the technical requirements, and you need to comply to all of those. And it will also list other requirements such as suitable notification at the ESCOM point of supply and metering installation. So this is for anyone coming to your installation, doing routine maintenance or other work, to be able to see that there is a PV installation. Then basic tests need to be done to verify the normal safety functioning of the installation and the embedded generator installed, and that the balance of the customer installation carries a valid certificate of compliance. And then sign off by a suitably qualified person needs to be done, and currently this is a professional engineer or professional technician that can sign off on an installation. So we have different system configurations. We have grid-tied systems. Here we have our PV panels, our inverter. This goes to our load. Through a meter, it's connected to the grid. We can also have a standalone system. The standalone system is not connected to the grid and typically have backup batteries. The backup batteries are used in cases where the sun is not shining. So when it's really overcast or raining and there's no electricity being generated, or typically at night time, so that you do have energy to use. This is what a typical solar PV installation looks like, where you have the PV array. This goes into a PV combiner box, combining all the arrays. Then you would have a DC disconnect, so you can disconnect the arrays from the inverter. Typically this is used for doing maintenance on the inverter side during the day. You can't shut down the sun, so you need to disconnect the PV from the inverter, and this is what the DC disconnect is for. Then you'll have an inverter. This is connected to the grid through an AC disconnect, which could be a circuit breaker. Grounding and earthing is very important, and we need to make sure that on the DC side we also do proper earthing and grounding. So grounding can be done in different ways, and PV array should either be ungrounded, negatively grounded, or positively grounded. Grounding is only possible with inverters that use transformers. The inverter manual should specify the grounding scheme to be used. So it's important to read through the manual when you do an installation and make sure that you use the correct way of grounding. Otherwise, you might compromise the working of instrumentation, or it might not work at all. The module frames and structures should be earthed, and this can be done on a separate earth that will be discussed. And this earthing of the structure and the PV frames is to protect against cable faults. And this is typically where a cable gets pinched between a structure and a bolt, and that you don't have leakage currents flowing somewhere where you don't want it. It's a safety issue. If the frame is live and you touch it, you might get shocked. There should be a clear path to ground for these currents to flow. So, as discussed, we need to ground the PV arrays, and this can be done by a different earth spike. On the AC side, we also need to connect the equipment to ground. So there's another earth spike, and typically outside your house there will be an earth spike that you can connect this to. It's very important that you only use one earth spike or connect this only to one ground. So this earth spike might be sitting outside of your house or the nearest Eskom feeder box. Apart from the grounding, lightning protection is very important because this controls the path of lightning after it hits. Fuses and breakers offer no protection because it was not designed for this, and the energy contained in a lightning strike is just too much. So to do this, all equipment must be bonded to a single protective ground point, avoiding the potentially large voltage differences between several grounds. So in some cases it might be easier to use more than one ground, but this might have the effect of those grounds sitting at different potentials, causing other problems. So use one ground. However, one ground rod might not be adequate, and this can be tested, and there is a certain grounding resistance that you need, and it might be required that you put in more than one ground rod and connect them to form a good ground connection. In addition to good grounding, we need surge arresters, and this is for lightning protection, and it gives a path for the lightning after it's hit the structure. Installation safety is important, and we need to take care. There are certain guidelines, regulations, like the Health and Safety Act, and we need to know that high voltage DC is lethal. And when working with PV arrays, we do have high voltage DC, and there's no on-off switches. Like I said, when the sun is shining, it's generating energy. So we need to minimize the likely exposure to this risk. We can do this by training our installation team to follow a specific order of connection, and this is normally done by start working on the wiring from the cold side towards the hot or the generator side. So you will connect wiring from basically the inverter side to the generator, which is the PV modules, and connect the return bin in panel strings last. So when you connect the last bin, the system will be live, and you need to take care of that. Use 1000-volt gloves where practical. It's not always easy to work with these gloves. They are thick rubber gloves, so you can't do fine motor things with your hands, and you might want to take them off, but you need to take care of that situation. No bare feet or shorts should be worn, and when you do an installation, a first aid kit should be close by. So there is the Occupational Health and Safety Act, and this is there for your safety. Make sure that the installers wear harnesses, straps and helmets, and beware of manually handling equipment that's very heavy. PV modules are typically 25 kilograms each, so if you want to load them faster, you will take more, and only loading 300 kilowatt modules will be 75 kilograms already, which is quite a heavy load. Take care of falling objects, and this is more for the installers, so they must keep the workspace tidy and attach tools to a person. If a plier falls off the roof and it hits somebody on the head on the ground, that might be a serious injury. Take care of dehydration. Installers are working in the sun, so take care of your people. If you are an installer, make sure they are hydrated, protected against sunburn, and also glare protection. Then, because we're working on roofs, you will typically have a ladder. Make sure that you set up ladders correctly. This is easily done if the ladder is long enough. We use a simple 4-to-1 rule, where if you stand at the bottom of a ladder and you hold out your hands, the tips of your fingers should touch the ladder. We should also make sure that the ladder extends the end of the roof by at least 1 meter, so you can easily climb on and off the roof. When we troubleshoot an installation, you should be careful and think about what you're doing. Don't replace a blown fuse without first finding the reason for the overcurrent. Then be sure not to mistake AC fuses for DC fuses. Typically at your hardware store you will easily find AC fuses but not necessarily DC fuses, and here we have a picture of something that happened when DC fuses were replaced with AC fuses, and AC fuses can't handle the overcurrent, and this was just a big arc and a lot of plastic melting and smoke. So make sure that you replace the correct items. Finding DC ground faults can be used by measuring the string open circuit voltage and then measure the string DC positive side to the ground and measure the DC string negative side to the ground. DC negative and positive should float at around half of the open circuit voltage and then decay to 0. If not, then there is a ground fault in the string, and the location of the ground fault is indicated by the fixed DC on the positive side or the fixed DC on the negative side. So this gives you an indication where to go look for the fault. If the DC positive or the negative voltage is not multiples of a PV panel voltage, and this is now the open circuit voltage, the fault is inside a PV panel. So this gives you some tips to look out for. Then DC cabling, MC4 connections that's not properly crimped can cause problems in the long run, although installation might be working sufficiently. When it's installed, over the long run connections can loosen, and this might ensure problems for you. Pinched cables between panel mountings and rails can damage the wires, and this can lead to ground or earthing faults. If you bend the wires too close or too small radius, you might get internal damage that will only become apparent in the long run. In the lighting areas where lightning strikes, we need to avoid conductive loops because this can induce large voltages and currents that damages equipment. All loose and unsupported cables should be taken care of in an installation. Typically, you would use cable ties to tie down cables, and as can be seen here in the picture, this is plastic cable ties that is used. When you're doing installation, plastic cable ties are okay, but plastic cable ties, when exposed to sunlight, would probably not last more than 3 to 6 months, so it is best practice to replace plastic cable ties with metal cable ties. In this cable tray, there's no problem using a plastic cable tie. Although this might decay and might go off, this cable tray that's on the roof will be closed from the top. So these cables will also not be exposed to any UV, as the same for the cable tie. In South Africa, we have an excellent resource, and PV is really a good option to supplement your energy at your house, your business, or your factory. And there's a vast industrial area that can use utilities. There's a vast industrial area that can utilize PV. Go green is a current mentality, and maybe someday soon we will have a carbon tax that will make it more financially viable to install PV. Solar PV is easy to install and require low maintenance, and it's suitable for urban and rural areas. Then we will discuss some frequently asked questions that I get often from people that haven't read a lot about PV, or it's not their daily business. And some of these are, what are the components of a photovoltaic system? Now, we've done this, so you should be familiar that a PV system is made up of PV modules or panels, an inverter for a utility grid connection, and then some wiring and mounting hardware or a framework for the modules. Question number 2 was, how long do a PV system last? And this really depends. A PV system that is designed, installed and maintained well will operate for more than 20 years. Our utility scale PV installations have signed contracts for 20 years. PV panels are warranted for 20 to 25 years. Just take care that inverters will not have a warranty for 20 or 25 years and typically have a warranty for only 1 year. You could buy extra extended warranties on inverters, but this will also cost more. So make sure when you compare inverters that you actually do compare apples with apples. The next question is, can I have photovoltaics to power my home and or business? Now, PV can be used to power your electrical system, including lights, cooling systems, and appliances. When there is no sun, you should, however, need to be connected to the electrical grid or have backup batteries. Make sure that if somebody tells you that you will be safe from load shedding if you install a PV system, that PV system can actually provide power when not connected to a grid. Or you might need a special inverter that can do that, but it will use backup batteries. So just make a note of that. Then how long does it take to install the average system? Now, for your average domestic system, depending on the roof and the accessibility, it might only take 1 to 2 days to install a system. The next question we have is, can I get paid for generating electricity? Now, the answer to this is a bit complex, and it really depends on the local regulations in place. So please contact your local municipality to find out. Etukwene municipality does offer a feed-in tariff. So make sure that you apply for the connection, and if you're compliant, you would be able to get a feed-in tariff. What is an export or feed-in tariff? Well, that is the payment or the credit that you received from the municipality for the electricity that you feed back to the network. This might not be, if you're working on credits, be a one-to-one, or the tariff, you might earn less than what you pay for electricity. So make sure what the exact tariff is when you do connect. What do kilowatt peak and kilowatt hours mean? So kWp stands for kilowatt peak, which is the nameplate rating of a solar panel. Kilowatt hour stands for kilowatt hour, kWh stands for kilowatt hour, which is energy. And this refers to how many kilowatts are produced in 1 hour. This is also the unit that you will be paying or selling electricity for. The next question is, does solar panels take more energy to make than they generate in their lifetime? And there's lots of myths around this. Research shows that the average panel will pay back the energy used to manufacture it in less than 4 years. And this figure changes slightly for the different technologies, like the wafer and the thin film PV modules. The next question is, how do you know that the system is taking power from the panels and not from the grid? Well, the way electricity works is like water, and it will choose the easiest path to flow. The system will automatically take power from the PV panels and will only draw power from the grid if insufficient power is available from the PV panels. So the electricity generated will take the easiest or the shortest path to the load, and the load in your house or your business will be the shortest path. So you will use the energy generated first before you export. Then, do PV modules lose efficiency each year? And the answer on this is yes. You will experience an average loss of up to 1% per annum. So this is important to take into account when you do calculations for warranty purposes. If your panel starts producing less power over 10 years, you have to take this into account before you contact the manufacturer to do a warranty claim. Are PV modules guaranteed? Well, some will be, some won't be. So make sure that you know which are and which are not, and that you buy from a reputable module manufacturer, because they provide guarantees, and these guarantees stretch between 20 and 25 years. Like previously said, the inverters, however, have a much shorter warranty period. Can I walk on PV modules on my roof? This is a typical question, and although PV modules are quite strong and it will take the loading, it won't break immediately, PV modules are not designed to be walked upon. And this could cause performance issues in the long terms, with micro cracks being created in the panel, and these develop further as time goes on. So that is the basics of a PV system and PV modules, how you connect them to an inverter and then put energy onto the grid. I hope you've enjoyed this course. Good luck with installing your PV.